Hey everyone, and welcome to this explainer. I am absolutely thrilled to have you here today. We're going to conduct a really deep, systems-level audit of the architecture that powers some of the most fascinating generative models on the planet. We aren't just going to stare at a bunch of math equations either. No, we are going to trace the exact operational flow of a system that literally learns how to imagine. Okay, let's ground this in the physical world first. Imagine an everyday action. You grab a pen and write a single digit down on a delivery form, say a number 5. It's tactile, right? It's just monochrome ink on paper. But the second that analog image is scanned, it transforms into a raw data intake packet. And for our infrastructure today, we're simply going to label this input packet X. And boom, we plunge right beneath the surface. This deep navy and cyan schematic represents the hidden learning system we're auditing, the Variational Autoencoder, or VAE. Now, this network doesn't just awkwardly memorize the exact pixels of your number 5. By processing thousands of these X packets, the system actually learns the underlying concept of the digit itself. It learns the slant, the width, the messy loops. So, to truly understand how it pulls this off, here's our system diagnostics menu for the day. We'll map the hidden learning system, check out the VAE coordination mechanism, audit the ELBO ledger, see generation without input, review system failure modes, and finish with our system evaluation checklist. All right, part 1, the hidden learning system. Let's move into our first diagnostic zone and map out the exact causal flow of our data packet. Everything starts with a strict causal handoff. First, our input packet X, that scanned digit, travels straight into our first named actor, the encoder station. We denote this as Q phi. The encoder consumes X and produces two absolutely critical outputs. It gives us a mean vector, called mu, and a log-variance vector, called log sigma squared. Together, these basically describe a probability distribution, a specific region in the latent space where this digit belongs. But here is our first amber warning. To actually make this system generative, we have to inject an independent packet of stochastic noise, called epsilon. Which brings us to part 2, the VAE coordination mechanism. Because, injecting random noise into a delicate learning pipeline sounds like a complete recipe for disaster. So how does the system handle this without breaking? Well, it uses a brilliant bypass mechanism. This is the reparameterization trick. Notice the central formula here. Z equals mu plus sigma scaled by epsilon. Instead of trying to sample directly from a random node, which would totally block our system's ability to learn, we formulate our latent sample Z by taking that independent noise, epsilon, scaling it by our standard deviation, sigma, and then adding our mean, mu. We are essentially externalizing the randomness. It's literally a structural workaround. If you look at the blocked stochastic path, if a system tries to update itself using backpropagation, the optimizer just hits that random node and stops dead. The gradients simply cannot flow, but by reparameterizing, we create a clear deterministic route. The gradient flows beautifully right around that injected amber noise, which means the network parameters can be continually updated by the optimizer. It's a real game changer. Okay, so with our latent sample Z successfully formulated and dispatched, it travels to our next major actor, the decoder station. We denote this as P theta. The decoder consumes the Z packet, and its sole job is to translate that compressed latent concept back into the physical world. It generates a reconstructed packet, X hat, and if the system is actually working correctly, X hat should look an awful lot like the original handwritten digit we started with. Part 3, the ELBO audit ledger. You might be wondering, how does the system know if it's doing a good job? Let's shift over to the system's internal accounting department to look at its objective function. So the VAE doesn't just have one goal, it actually has two, and they're managed by the evidence lower bound, or ELBO. I like to think of this as a two-ledger audit. On the left ledger, you have reconstruction pressure. The optimizer updates the network to ensure the decoder accurately recreates the input. Pretty straightforward. But on the right ledger, we have KL pressure. This is an amber constraint, a regularization term that forces the encoded distributions to group neatly together and resemble a standard normal prior, P of Z. The optimizer is constantly running a tug of war to balance these two competing ledgers. When that KL pressure is applied perfectly, our latent space becomes beautifully organized. You get similar data points clustering together in smooth transitions. Now, I need to be absolutely clear about something. What we're looking at is an explicitly illustrative toy view. It's a 2D density contour map just to make the concept digestible. Real VAE pipelines, they operate in vast, mind-bendingly complex, high-dimensional spaces that we couldn't possibly visualize on a flat screen. All right, moving to part 4, generation without input. This is where we get to the really fun stuff. What happens when we completely shut off the physical intake? No input X at all. This is the true generative magic of the VAE. Because our KL pressure force the latent space to resemble a standard normal prior, we can actually just bypass the encoder entirely. We literally just sample a latent vector Z directly from that prior, P of Z, basically pulling it out of thin air. We feed that raw Z into the decoder station, and the decoder synthesizes entirely new hallucinated data. It generates a digit that looks completely real, but was never ever written by a human hand. Part 5, System Failure Modes. Of course, any complex infrastructure has its breaking points. Let's trigger our Coral Red incident report and analyze what happens when this whole mechanism breaks down. So what happens if those constraints are miscalibrated? Well, we have a few known failure modes. First is weak prior alignment. If the KL pressure is too low, the latent space fractures into fragmented territory. If you try to sample from it, you just get pure garbage. On the flip side, excessive regularization happens when KL pressure is too high. This completely washes out the input details, giving you super blurry outputs. Then there's the dreaded posterior collapse. This is where the decoder becomes so powerful it completely ignores the Z packet altogether. We can also see approximate posterior mismatches, where our Gaussian assumption just doesn't fit the data's true shape. And finally, semantic disentanglement failures, where changing one specific trait, like making a digit thicker, accidentally changes its slant too. Finally, part 6, the system evaluation checklist. Let's get things back to a stable state. How do we know our system is actually healthy and ready for deployment? We always run it through our final diagnostic checklist. Number 1, reconstruction fidelity. Does our output X hat reliably match our input X? Number 2, prior sample quality. When we sample out of thin air, do the hallucinations actually look real? Number 3, latent utilization. Is the decoder actually relying on our Z packets, proving we avoided posterior collapse? And 4, task-specific utility. Does this structured latent space actually help us do downstream stuff like classification or anomaly detection? A healthy VAE perfectly balances all of these points. Before we wrap up, I want to leave you with a bit of a provocative thought. We talked about semantic disentanglement as a failure mode, that struggle to perfectly separate concepts in the latent space. As we build more massive, complex models, you really have to ask, is guaranteed flawless separation of concepts actually a solvable infrastructure problem? Or, given the messy, naturally entangled reality of our physical world, is perfect disentanglement just a mathematical illusion? It's a huge question, and it's something the absolute best minds in generative infrastructure are still wrestling with right now. Thanks so much for joining me on this explainer, and I'll see you in the next one.